So previously we talked about block diagrams. We also talked about transfer functions and O.D.Es. Now we want to talk about the fourth way to describe a system or to model a system, which is called state space representation. So the main motivation behind using state space representations is a problem or a weakness that Laplace transforms create, or actually problem with transfer functions. So we studied Laplace transform, which gives us the power to write an ordinary differential equation as a transfer function, and we said we like that because it turns ordinary differential equations into an algebraic equation, which is easier to solve. But we are going to see a limitation that this method has, and therefore in 1960s or 50s people started thinking about another way to write or model a system, an alternative way to model a system, which is state space representation. Okay, look at these two obviously different differential equations. They look different. Mathematically, they are different if they are representing a physical system like a circuit or a mass damper spring system. Obviously, the number of masses, the number of dampers, the number of springs is going to be different. So we have different systems, system 1 and system 2. Now let's write transfer functions for them. Can you write transfer function of the first system? Well, we take Laplace transform. On the left-hand side, we are going to have s times y1. And then we assume that the system is at rest, no initial condition. So I'm going to have s times capital Y1 plus capital Y1 equals to capital U1. So then if I factor the left-hand side and then write it as y1 divided by s1, I'm going to get 1 divided by s plus 1. That's the transfer function of system 1. How about system 2? If I want to write the transfer function for system 2. Well, similarly, I take Laplace transform of both sides. I'm going to have s squared y2 plus 0.5s y2, and here I have 0.5 y2, and so this is y2 and this is y2. It's typo. And then I have s times u2 negative 0.5 u2. So then if I write down the fraction, the transfer function, I'm going to have s negative 0.5 divided by s squared plus 0.5s negative 0.5. I can write the denominator as s plus 1 times s minus 0.5, then this s minus 0.5 and this s minus 0.5 would simplify, and what's going to remain is 1 divided by s plus 1, okay? Which is what I had here too. So we got the same transfer function for two obviously different systems. Okay, what does this mean? This doesn't mean that system 1 and 2 are the same or like identical. Obviously they are different. It means that the tool you're using, the mathematical tool that we are using to describe our system, is not good. You know, the mathematics that we use has always limitations, and this is showing us that the math here, Laplace transform, is not perfect. It has limitations. Okay, so let's compare state space representation and transfer functions before we actually start describing what state space representations are. So, transfer functions, what is good about them is that they turn differential equations into algebraic equations and make problem easier to solve. What is the con? It's what we just talked about. It's called zero pole cancellation. Zero pole cancellation is causes problems because there's information that is being lost, and the information is inside of the system. When you simplify the numerator and the denominator of a fraction, that information is lost. In mathematics, that's something that in middle school we learn, but that is not a good thing here because you are forgetting what is happening inside of the system. So the alternative is state space representation. Information isn't lost. It's like the definition of a state is as if you're defining or labeling parts of the system that you care about, and you're going to keep track of them. What is the con? What's the problem with state space representation? These labels are up to you, and therefore there's infinitely many ways or infinitely many state space representations for the same system. So every one of us can write down a state space representation which all look different, but they're all describing the same system. So for that reason, to address this issue, people have created standard forms to represent the system. So people have said, okay, you know what, if you want to write down state space representation, how about we define standards and say this is called, and then there are names. Here we are going to study controllable canonical form, which is a special format of state space representation. The general idea is to write our ordinary differential equation as this. So you have a differential equation and you want to write it down as equation 5 and equation 6. These are matrices and vectors. X, U, Y, are all three of them are vectors. So U is the input. In this course, we assume that we have only one input, so U is actually a vector with one element in it, so it's just a function. Y is the output. Again, in this course, most of the time we assume that we only have one output, so Y only would have one element. But X is the vector of states of the system, and it can have multiple elements. This slide is describing the general idea behind state space representation. That's why U and Y are having multiple elements in a vector. But for our course, for automatic controls, we have most of the time only one input and one output, which means that the dimension of Y and U would be 1. So, what are the steps to write state space representation from an ordinary differential equation? Well, number 1, you use the variable of the differential equation, if it's Y or it's whatever is the variable in your differential equation. You use that to define your first state. So I want to show my states with x1, x2, x3, x4. So I assign y to be x1. So what I'm saying is that the first thing I care about in my system is, or the first label goes to y. I want to keep track of y. Then I put my other states or other labels, I give them to higher orders of the variable of the differential equation. So here y is the variable of the differential equation, therefore y dot and y double dot, and if I have higher orders, I label them as the second state, the third state, up to one less than the order of your O.D.E. So if your if your differential equation is a third order differential equation, you do that until y dot or y double dot, one less than your the order of your ODE. We are going to see an example and it's going to be more clear what I'm saying. Then you bring all terms to one side with the exception of the term with the highest order. And then we use this equation and other equations that are generated from this equation to write everything in vector matrix format. So I know it's confusing. In this course, seeing examples, numerical examples really helps. So I have this differential equation. What's the variable of the differential equation? It's y. So I keep track of it. That's my first label. I call that x1. And y dot would be x2. So I start assigning these labels to my variable until one less than the order of my differential equation. This is a second order differential equation. So I don't want to label this, but I label everything else. So y would be x1 and y dot would be x2. Now I bring everything to one side of the equation, and so I'm gonna write 3y double dot equals to, so here you see I'm substituting, y would be x1, y dot would be x2, so then I bring them to the other side, I'm gonna have y double dot, and I'm dividing both sides by 3, I'm gonna have y double dot is negative 2/3 x2, negative 4/3 x1. Okay, now this is one equation. I have x1 in it, I have x2 in it, and I can also use x2. I defined x2 to be y dot. Therefore, this would be x2 dot, right? So now I can use this equation and substitute it inside a matrix vector relationship. So this equation would be the second row here. Look at the second row. X dot 2, which is y double dot, is equal to negative 4/3 x1, negative 2/3 x2. So remember, in matrix vector multiplication, you take the first row of the matrix, multiply it element-wise to your vector, so 0 times x1 plus 1 times x2, that's going to be your element on the left-hand side. Then you go to the second row, you're going to have negative 4/3 x1 plus negative 2/3 x2 is y double dot. So that's how matrix vector multiplication works. Now, okay, that was the second row. How did I write the first row here? Where did I get 0 and 1? I'm claiming 0 times x1 plus 1 times x2 is y dot, which is x1 dot. How did I write this down? Well, from the definition right here. Y dot is x2. So y dot is 0 x1 plus 1 x2. So I use this equation, and I use this equation to write my relationship here. And this matrix is my A matrix. This is the x vector, and this is x dot. So I wrote this first line here, x dot equals to ax plus bu.